Thank you, Joel. Okay, so let me just start with a few words on motivation for the problem we are going to discuss. So because I see that the audience is really specialist, so I will be rather brief, and half of my talk I will be brief. But nevertheless, it will take still half of my talk. Okay, so let's start with Soundness conjecture, which is just orthogonality of the Möbius function. The orthogonality with all continuous observables coming from a dynamical system of zero entropy. Okay, so the Möbius function is orthogonal to all deterministic sequences. All sequences are bounded by assumption. Here's the first question, which looks quite natural. Namely, so in this conjecture, we consider Möbius function, which is a multiplicative function. So you can ask yourself, what happens when we replace this Möbius function by a different multiplicative function? So say u, and when I'm talking about multiplicative functions, so they are by definition bounded by 1. Okay, I will not be stressing this in what follows. Okay, so now the problem becomes as it was before, right? With mu replaced by u. And well, we would like to know what is it reasonable to think about this problem. So first, let's just consider well a simple replacement. Like we replace the Möbius function by a friend of it, the Liouville function, and so there are two ways to show that problems become equivalent. So one is I just took from the introduction of one of the papers of Terry. And it's just to use, okay, so I look at the expression for the Möbius function. And we use some identity between the Möbius function and the Liouville function. So you can see it here. Then some simple manipulations, and we change the order of summation, and we arrive at this formula here. So now you see if D is small. So well, maybe the first observation is that, well, for each D, the entropy of this T to the D square is still 0. And if D is small, when you look at this part of expression, so you see that we have something like Soundness conjecture with the Liouville function. And because, well, the series which we have here is just absolutely summable, so then it works. So in other words, Liouville orthogonality implies Möbius orthogonality. And the other direction, it also works. It's even simpler. Oh, excuse me. You just use the identity of that part. So one can ask yourself, okay, but what about dynamics? Is it possible to give a dynamical proof? So the answer is yes. At least one direction can be proved using dynamics. I will not give this proof because it's a little bit long and involves something. But in fact, this proof shows a little bit more. And you can see this footnote here, that this proof seems to contribute to the following natural question. So suppose that we have two multiplicative functions, and we consider the situation that one pretends to be the other one. Okay, so we consider the multiplicative distance, and suppose that this multiplicative distance is finite. So is it true that Soundness conjecture for one of these functions implies the other one? So this is in some cases using dynamical proof. In some cases, you can prove that this really holds. I don't know what is the answer in general. Is this true? Okay, but let's just go back to the topic of this talk. So our question is, what happens if instead of mu we consider any multiplicative function u? So what is a necessary condition? A simple necessary condition to obtain orthogonality? Well, of course, periodic sequences are zero entropy sequences are deterministic sequences, we have to be orthogonal to all periodic sequence. So this is one obvious necessary condition. And because we are considering the multiplicative case, so we say that the function is aperiodic if this is orthogonal by definition. It's orthogonal to all periodic sequences, and equivalently, it is the case that the mean of the function along any arithmetic subsequence is equal to 0. So now the question is it realistic to expect that if U is orthogonal to all periodic sequences, so then it is orthogonal to all deterministic sequences. So if you drop the assumption of multiplicativity, so of course it makes no sense, right? It's just easy counterexample. We know that that's very far from being true. But what happens if we really consider the multiplicative world? So the question is, what does number theory tell us about all that? So let's see. So I just recall, we have Chowla conjecture from 1965, which tells us that all autocorrelations of the Liouville function are equal to 0. So then Chowla conjecture implies Soundness conjecture. Okay, here is just the Liouville case. And we'll be mainly considering functions which whose values are in the unit circle. So you may ask, what is Chowla conjecture in this case? So here is we need a word of explanation, right? Because you see that the expression looks more complicated than this one. We have powers, but the reason is very simple, right? I'm tacitly assuming that the function u, if I look at the values of the function u and also of its powers, so they are really essentially in the circle. I mean, there's no closed subgroup of the circle such that the values are taken in a smaller subgroup. If you have a smaller subgroup, then you reduce the number of polynomials to be considered. Simply. And then also in this case, Chowla conjecture implies Soundness conjecture. Okay, so then there was another conjecture in the 90s, namely the Elliott's conjecture, which looks a little bit like a Chowla conjecture, but you see that in this situation we consider not only one fixed multiplicative function, but we have many functions. And what we assume, also there are some mild assumptions to exclude easy counterexamples, but basically we consider this kind of expressions, and we assume that on one coordinate we see a function which is aperiodic. Okay, so this is Elliott's conjecture. So now the impression is that it was completely reasonable to. Okay, well, I should add that Elliott conjecture implies Chowla, Chowla implies Sarnak, so Elliott implies Sarnak. So then it looks that it was completely correct, right, to assume that if you have aperiodic functions, so then we should expect Chowla in particular, right, because even Elliott holds. But as far as I know, nobody ever asked this question. And well, which is quite meaningful, right? Especially for somebody like me, who is an outsider, not a number theorist. So there was no such a question. And then in 2015, in fact, Elliott's conjecture was disproved in the paper by Kaisa Matomäki, Maxim Radziwiłł, and Terence Tao. In fact, so what they show that already on the level of correlations of length 2, you can find a counterexample. But then it was continued in the sense that, well, they improved Elliott's conjecture just by just putting some more assumptions, some stronger assumption on the function, on the function u, which appears here, right? Aperiodicity, which is what some people call strong aperiodic functions, and for that this strong aperiodic functions where the conjecture in this generality is still open. Okay,
What's strongly aperiodic?
So then so you have to look, that there is this distance. Aperiodic means that the distance to any skewed Dirichlet, you take products of Dirichlet character and Archimedean character, and you look at the distance between from your function. You expect this to be infinity. This is just aperiodicity. But then there is a condition. Somehow, how quickly it goes to infinity. Okay. So let me just to continue. We need.
So this corrected one is the low one.
It is the low, right? Of course, there are some cases which are.
Right, for two Chowla, if you logarithmic average, the log an average version, there's some average versions that are true, but the non-average versions.
Okay, so let me just briefly, especially this is just to introduce notation, briefly recall some basic notions in topological dynamics. So in topological dynamics, we consider homeomorphisms of compact metric spaces. So if we want some basic examples of topological dynamical systems, we consider so-called subshifts. To speak about subshifts, we need a compact alphabet. Often it's just finite, and we will be assuming that we take an alphabet which is contained in the unit disk. But we will, in fact, most of the time we will be interested in the circle as the alphabet, so it will be continuous alphabet. And then, okay, so we take the space of all decided sequences on which we have a homeomorphism, which is just shifting the sequence by one position to the left. And so then we obtain a dynamical system, so-called full shift. And we can also speak about subshifts, which is just to take a subset, which is closed and as invariant. And then the restriction of the shift to X, it gives us dynamics. Okay, so how to obtain a subshift? Well, a simple way to obtain a subshift is just to take one sequence, which you see here, and then you take the orbit of it, which is obviously an invariant set, and then we take the closure of it. So that's the subshift determined by the sequence. Suppose there is this issue, one-sided, two-sided. So because usually in number theory we have one-sided sequences, you can complete, for example, by symmetry, if you like, but well, Nicolaus, he likes to put zeros, right, everywhere in his paper. Anyway, so for example, if we take the Liouville function, so what do we obtain? So the values are +1, -1. So the alphabet is +1, -1. And then, well, we symmetrize it, and then we obtain we treat now the Liouville function as a point in that space with a equal to 1, -1, 1, and we obtain a subshift. This is the Liouville subshift. Okay, so this is topological dynamics, but to pass to ergodic theory, we need invariant measures. We need measures which are invariant under our homeomorphism. So we have a homeomorphism of a compact metric space. So on that space, we consider the space of probabilistic Borel measures, which is itself compact when we consider the weak star topology, because we have the action of our homeomorphism, so we can consider T-invariant measures. So that's a closed subset, and which has an additional structure, affine structure, and the external points of this affine subset, these are exactly ergodic measures. So to see that this set is not empty, so the simplest way to see it is just to consider so-called empiric measures. So we just take a point x, little x in our space, and then we look at the orbit of it. First, we consider this initial interval of this orbit, and we distribute the measure on that finite set, and then we average. So this gives us, okay, it has to converge along the subsequence, and the limiting measure will be certainly an invariant measure. So then, the vocabulary is that we say that point x is generic for a measure if the whole sequence converges. So I just recall what it means, but this is just to recall for those who forgot what is the weak star topology. So we have this convergence, and if the convergence takes place, which is often what happens, so then we speak that the point, then we say that the point is quasi-general. So now the crucial notion. So we have, so again, we have a homomorphism T on a compact metric space, and we have a point X in that space. So now we look at all measures we can obtain by averaging, this initial parts of the orbit. So this is a certain set, which is closed. And let's just think about measures in this set as visible measures, visible from the point X. Okay, so that's one thing which is, of course, in dynamics, this is standard. What is, I believe it's standard in number theory, but in dynamics, there was a kind of surprise that we can also consider a different way of averaging. And this logarithmic way of averaging gives us, so now, the points are not equidistributed, okay, when you take the initial point, but you have weights. You have weights, and weights are 1 over n. So now you divide by the sum of these weights, and you can check, it's a nice exercise, that the limiting measure, it will also be invariant. So then we can speak about points which are logarithmically visible, we can speak about measures which are logarithmically visible from a point. So one thing to be remembered is that whatever we take, these visible points or logarithmically visible measures or logarithmically visible measures, so the set of these measures is either just one point, so the point is generic, but if not, so we have to have a connected set, so it has to be uncoupled. So there are many. And the crucial definition is that suppose that we have a sequence, okay, so this is not necessarily a multiplicative sequence, it's just one bounded sequence. So we treat this sequence as a point in the subshift it determines. And then we take this construction. We consider measures which are visible from that point, either Cesaro averaging or logarithmic averaging. And what we obtain is a measure theoretic dynamical system. So all these systems are called first-order systems of this arithmetic function. Okay. So now, once we introduce this language, we can see that Chowla conjecture is nothing but the fact that the Liouville function is a generic point for the Bernoulli measure minus 1 with the alphabet -1, So of course it implies in particular that the Liouville subshift is just the full shift. And this is unknown, right? Talking what happens if we know that Chowla holds. So similar observation takes place when we consider, let's say, functions taking values in an essential way, taking values in S1. So we have the same story, right? So if we assume Chowla, so Chowla is something that there is only one Furstenberg system, and this Furstenberg system is very particular. Namely, this is, well, in these situations, it's just how much on the infinite dimensional. So in this case, infinite dimensional terms. Okay. So now there are questions. So we may ask, okay, so what can we say about Furstenberg systems of general aperiodic multiplicative functions? So what is the entropy? Is it true that the entropy is positive? And then the question, well, maybe the most complicated one, does Chowla hold along a subsequence? So notice that this last question we can formulate. Well, maybe I should be more precise what we mean along a subsequence. So we want a universal subsequence for which all the correlations, they behave the way we wish. Okay, so here it's just vanishing of all correlations. Okay, so this question, especially the last one, was an official question of the workshop we had. If you, it was almost 5 years, well, 4 or 5 years ago.
Pre-COVID and post-COVID are the only time skills these days. Yeah.
So, okay, so that's. So I wanted to recall some more conjectures. I was recalling Chowla, Elliott, but in the this extremely beautiful paper by Nicolaus and Bernard on Soundness conjecture in case logarithmic Soundness conjecture in case of systems for which we don't have too many ergodic measures, they also formulate some conjectures. So I just chose some. These are not exactly all of them. So for example, what their conjectures predict is that if you take a multiplicative function which is real, so then it has just one Furstenberg system, and this Furstenberg system is of the form it's up to isomorphism, measures theoretic isomorphism, is direct product of an inverse limit of cyclic systems and a Bernoulli system. And so it's even a more precise statement if we take values +1, -1. So here we hope to obtain that each multiplicative function with such values. So it has also only one Furstenberg system. It was already A, but this Furstenberg system is very particular. It's just product of Bernoulli and an ergodic odometer. But because this is the real case, so in the paper I already mentioned by Matomäki, Radziwiłł, and Toruń, so they prove that if you have real valued aperiodic functions, so that they are strongly aperiodic. So these two A and B, they consider that they treat with strong aperiodicity. So for the moment we don't know what happens, but there was also a conjecture, general conjecture concerning complex valued, let's say, S1 valued multiplicative functions, and here they conjecture predict that, well, so now we don't know what is the system and how many systems we have, but the only thing we insist on is what are ergodic components. Okay, so we want to present our Furstenberg systems as generalized affine, as generalized convex combinations of systems which are products of this procyclic and Bernoulli. Okay, so that's what we have. So let's just illustrate of what was said so far on a very simple class of completely multiplicative functions, namely these Archimedian characters. Okay, so what is an Archimedian character? So that's this kind of function. So it's indexed by this. The family of these functions is indexed by all real numbers. And let's say explicitly that these are not aperiodic functions, right? Do you see that? Well, we have this formula for the mean, and which means that the mean does not exist simply. Okay, so that this is very classical. Also, this is a kind of obvious observation. So in other words, Archimedean characters are so-called slowly varying functions. If you take the difference between two consecutive values, so with n going to infinity, you're going to 0. So of course, if we have this property, so the more we have the mean value property. So this we like, right? Mean slowly varying functions. It looks as if I'm just exaggerating because, well, there are many functions of that kind. But so why do we consider Archimedean characters? But it's maybe a little bit surprising, maybe more than a little bit, is that if we stick to multiplicative functions, so the only multiplicative function, well, taking that, this is important, taking values in S1, the only multiplicative functions which are slowly varying are Archimedean characters. But we introduced these Furstenberg systems. We would like to see, hey, we want to look at our multiplicative functions through this kind of eyes, right? So the proposition is that if we have an arithmetic function, so it's not necessarily multiplicative, so we have an arithmetic function, so this function is mean slowly varying if and only if it's Furstenberg systems. You can have many Furstenberg systems, we'll see in a while, but all of them from the dynamical point of view are identities. I wrote the first, you see that I wrote the first time that, well, it's isomorphic to the identity, but isomorphic to the identity means equal to the identity. Anyway, so let's see how it goes, because well, one direction is very easy to show. Okay, so we take a Furstenberg system. So in other words, we assume that we have a sequence of empiric measures which is convergent. Okay, so once I have this new, maybe I should stress this. Once I have this new, I have a natural. Each Furstenberg system gives me a natural stationary process. Namely, I have projections on coordinates because we are in the shift space. And once we are in this shift space, we have these projections, and this process is stationary because that's exactly the same as saying that this measure is invariant, but it is, right? Okay, so in other words, so now we have a bunch of stationary processes. So now I want to say what is a relationship between Z0 projection on the zero coordinate and on the first coordinate. Well, so let's compute the mean, but because well these are continuous functions, right, by definition, so I can compute it using my generic point or quasi-generic point, right? It's quasi-generic along this subsequence and so it's this, but this is zero by assumption because we assume that our functions mean slowly varying. But how can I have that this is equal to zero? Well, the only possibility is that Z1 is equal to Z0, but then Z2 is equal to Z0. So in fact, it's just Z0, 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 etc. Or if you want to see it, remember that we are on this infinite dimensional torus. It means that the measure which we consider is just concentrated on this large diagonal. Okay, so S is equal to the identity. So what happens if we take n to the I? Okay, so the story, I mean, we have to see what we have seen, right? The only possibilities are identities. But what are these identities? Well, so in fact, so now we have a measure which is on infinite dimensional torus, but it is on the diagonal of this infinite dimensional torus. So in fact, I can choose just the zero coordinate, but on the zero coordinate, I see the circle. So I have the circle, and what can I compute? Well, on this, so I want to recognize what is the measure on the circle. But to recognize what is the measure on the circle, it's enough to, if I'm lucky, of course, it's enough to describe it to Fourier transform. But the Fourier transform, because I'm on one coordinate, I will just compute by using Z0, the mean of Z0 to the power K, which is just the sum. We started with this, but I will just compute simply the value as the limit when I put here a little k, which is the k is Fourier coefficient, and then I know what to do, right? I have these numbers. Along the subsequence, I have to assume that it converges to a constant. And because log n is dense, so then I will obtain all possible constants. And I will obtain the Fourier transform of a measure. And you can in fact from the form of this Fourier transform you can just guess what is the density of the function. So in fact, what is the density of the measure? In fact, the measure which we obtain is equivalent to the Lebesgue measure. The density is something like exponential 2 pi x, and it's normalized. And then you have to take all possible shifts of this measure. So you see that you have uncountably many measures. No one of them is a Lebesgue measure. That's interesting. And it's interesting because, well, in the paper, so I already mentioned the paper by Nicolaus and Bernard Haas. So they computed what are logarithmic systems. Archimedean characters, and they obtain that there is only one, which is just Liouville measure on the circle. Of course, in reality, it's just infinite dimensional torus, and the diagonal is infinite dimensional torus, but you're only interested in what happened on the one coordinate. So here's a situation which we somehow keep in mind, that Furstenberg systems and logarithmic Furstenberg systems, so the sets can be even disjoint. So which is maybe kind of a little surprise. So now we'll finally, I think it's 2:30, so which is half of my talk, and this is 15th page. So finally, let's go to the main subject of this talk, which is to say we try to say something about a class of counterexamples to Elliott conjecture from the paper of Matomäki, Radziwiłł, and Toruń. So let me just recall the definition. I'm taking the completely multiplicative version of what is in the paper. So a completely multiplicative function, you see, taking values in S1, is in this MRT class if. So first of all, we have the sequence Tm, which will be a kind of a threshold. You will see in a while. So we have Tm and we have Tm plus 1, and well, this is a rapidly increasing sequence of positive integers. But then you have the second parameter, the second sequence Sm, such that, well, we have this relation. And then on this sequence, on this interval, well, we need to define what are the values at the primes. This is a completely multiplicative function. So this is this number. Okay, and what we want to see is that, so for the previous, for small p's, we want to say, okay, so I have this Sm plus 1. So of course, I shouldn't count that we obtain the values which is already somehow seen. The only hope is that we will see it with a certain precision. Okay, so if you see the picture, because now the procedure is just if you want to make sure that.
Sorry, is this the detail? Is this how they made the construction of the counterexample too?
Yes, this is one. Up to, let's say, mu squared, right? But that's the same. Okay. So you see, so we have a sequence. So how to construct such functions, or how to show that such functions they do exist? Well, so we have this sequence Tm, and let's say the construction is by definition. So we assume that Tm is given, and we know what are the values of our function for small p's. So what do we do after? Okay, so the next step will be to determine what is S sub n plus 1. And to say what is S sub n plus 1, maybe I should go here, because it's written. So for that, we consider this Cartesian product, which is, so it's finite dimensional torus, whose dimension is just given by this Tm, this parameter which I wrote down. And on this torus, we consider a certain rotation. And the rotation, let's say in the additive notation, it would be rotation by log p on each coordinate. But now we have a rotation on log p. So these are numbers which are linearly independent over integers. So then the rotation is ergodic, or well, if you are not in dynamics, so we can say, well, we have equidistribution property, so we can approach any point in the torus of dimension t sub n. But we have these values u of p, which we are interested in. So this is a very complete point. So we can find, because well, rotation is ergodic, so we can find this Sn plus 1, so that we can approach the real genuine values of the function p with the precision which is of that kind. So they really exist. Then you can show that somehow the growth of this Sn plus 1, if you compare this Sn plus 1 against Tm. So this must be super polynomial. So we saw here this thresholds Tm and Sm+1, Sm+1 squared. And well, maybe I should have read this also, that if you know that this is weaker than a super polynomial, so in fact, we obtain, for sure, we obtain an aperiodic function. Okay, so the picture which we see here, so this is Tm+1, Sm+1, Sm+1 square, but we have more numbers, right, which perhaps are interesting. It's not clear why I introduced these powers, right? We'll see now why. Okay, so that's
Just starting.
So that's the let's see the main result of the paper. So assume that what we have a function which is in this MRT class. So then for each D, there is a Furstenberg system for this function U. So this is measured on this infinite dimensional torus, UD, which is, so this Furstenberg system is isomorphic to the following unipotent system. Okay, so we reverse the order here of coordinates. So that's on the first coordinate, you see that this is just the identity, and then on all other is just summation of two consecutive values. So we are on the torus of dimension D+1. And this is equipped with D+1 dimensional Lebesgue measure. I think, yeah, it's a footnote which is here. So it's measure theoretically isomorphic, which means that if I take my process, right, this new D gives me a process. Each Furstenberg system gives me a stationary process. So this process will be exactly the same, so in the sense of processes, which means distributions. So this stationary process will be exactly by taking this function and just, well, the natural process which we obtain in the dynamical system, in this unipotent system, equipped with Lebesgue measure.
And ask you on the base, if you want, you can make it to be non-Lebesgue, or it will always be Lebesgue.
That's the main result. Well, it's a kind of very interesting question. And you're right. The answer is yes. And yeah. Well, anyway, so okay. So the first thing is that we have some. Since non-trivial Furstenberg systems, right? And furthermore, it follows that we have a Bernoulli shift as a Furstenberg system. So in other words, indeed, Chowla conjecture holds along a subsequence, and in particular, well, the subshift determined by these MRT functions, these are full subshifts, just the full shift, and the entropy is equal. So these functions, which we defined as locally, using locally Archimedian characters from zero entropy, I should have said that, but this is evident, right? That Archimedean characters, they are of zero entropy. And while here we just jump and the entropy is equal. But you shouldn't be so much surprised that the entropy is infinite. Well, the point is that we deal with continuous alpha. That's the reason. Okay. So let's see. So one thing, how did we get this this Bernoulli measure or this Hahn measure? So in fact, we didn't get it by showing, well, along such a subsequence, you get Hahn measure. No, the reason to obtain Chowla conjecture along a subsequence is that we have sufficiently many unipotent systems as Furstenberg systems. Because the reason is that so this is just a very simple algebraic system with Lebesgue measure, but you want more, right? And you have a very simple function, very natural function, a character, and you look at the process given by that, you can show that this process is, how do you say, is D independent. So let's say the first or any D different variables, they are independent. So in fact, so this is a very simple system, but in fact, well, it displays some kind of independence, and because we have this almost independent or more and more independent processes, and we consider the weak star topology, so we can pass to the limit, and the limit must give us how much. Okay. I think that's what I was already explaining, and all other things are I also was explaining.
So we said within a single multiplicative function, you can find all these for every D, or for every D there exists a multiplicative.
No, this is all these systems, they appear for any function of the class.
For
any function of the class. Okay, so what are the properties of this? Right, so in the paper, well, so Terry and his collaborators, they show that Chowla is not satisfied, but of course, if Chowla is not satisfied, doesn't mean that Soundness is not satisfied. But Soundness is not satisfied. Soundness conjecture is not.
Very hard to satisfy me.
Okay, so, and to understand what's happening here, so we want to see that this is, that Soundness conjecture is not satisfied. Well, we should point out a zero entropy system. And okay, so we take this U, and the point is, where is the entropy, in fact, sitting in this sequence? And you can see that the entropy is just sitting at these thresholds, which are right. So it's always produced there. If you go from Sn+1 to Sn+1 squared, so then there will be no entropy there. And in fact, you will see that the phenomenon that the only invariant measures you can obtain is just the idea. I mean, the system which you obtain is just the idea that no entropy is produced. So because, well, Sn+1 is much smaller than Sn+1 plus squared. So I'm just producing my zero entropy system by just taking constant value on what is preceding Sn, right? So I will have a slowly varying function, which is of zero, which will be of zero entropy, and which will correlate with our sequence.
Strictly speaking, there are two Soundness conjectures. I think with this one and then this one that basically is a full entropy or something. Did you propose two conjectures?
No, I just, my observation was just that if you zero entropy, you should always linearly disjoint. I think the full entropy is the strongest statement.
Right. But I mean, these, do you know if these functions have full entropy?
Really, these functions, they are of infinite entropy.
Right. Oh yeah, of course they're continuous. It doesn't make sense like you said. Yeah, no way. Okay, so.
So one more observation is that, well, we have this famous breakthrough theorems on convergence on short intervals for many multiplicative functions, but let's say strongly aperiodic functions, and you have no chances to obtain something like that for aperiodic functions. And it's, in fact, the only thing is just to show that we cannot have strong convergence, convergence on short intervals. It's enough to know that the identity is a Furstenberg system. This will violate short intervals, possible short intervals convergence.
I mean, to be exact to Terry's question, for Mobius or lambda, I did in the end of my note, I just wrote 10 pages of this, but I did write at the end this language that I thought it was Bernoulli genetic, Bernoulli, which of course means full entropy. Just in, yeah, so I did state that. I mean, I was completely motivated by Furstenberg's disjointness of K systems with zero entropy.
Sometimes we spend, okay, but this was everything about Chowla and Cesaro averaging. What happens if we take logarithmic way of averaging? So logarithmic Chowla conjecture also holds for these functions. I wrote the proof, but I think that the time is running. So, excuse me. Oops. But I will just explain to you what is behind that. Well, of course. So first of all, you just write that if you take logarithmic averages, so you can represent logarithmic averages as Cesaro averages with logarithmic weights. Or if you like, these are convex combinations. Maybe this is also enough to say that these logarithmic averages are convex. This is a convex combination of Cesaro averages. But the point is that this Cesaro averages, you have to go back. You see, this is indexed by this little n. So in general, this is what causes that in general there are no relations between these sets. But here the situation is a little bit different. I was showing you this thresholds, and so this was something like this: Sm plus 1, Sm plus 1. Well, it was Sm plus 1, and then we had these powers Sm plus 1 over. What should I put here? D plus 1. Sm plus 1 over d, and then the point is that this Cesaro averages, they are more or less constant on small or large intervals between these thresholds. So that's why. So it looks as if you have this, very unpleasant things to be computed, but if you know that this function is locally constant, so then you can say what's happening, and you see that. So at the end, when you arrive, so you obtain that this kind of measures are logarithmic systems. So I am not able to show that Cesaro Furstenberg systems, they are somehow also seen as logarithmic systems because you need here infinitely many measures, but you see, because you start with some parameter d1, so these are still, if I take the first capital D1 variables, so under this each measure, it is just the vector is just independent vector. But because it's and now I'm taking convex combination is the same, and I see that these vectors are independent in the limit that they will also be independent. So in other words, still this phenomenon of having more and more independent processes, it gives us, and you pass to the limit now is taken with respect to this D1, and you obtain. So now while this is fun, you can come back to conjectures which were formulated at the beginning. So you remember that the conjecture C by Nicolaus and Bernoulli was telling us what is the form. So we take the logarithmic systems, and we would like to see what are ergodic components of the systems, and it seemed that they should be of the form product of Bernoulli and procyclic system, but that's not the case, right? Because if you consider this kind of systems, you will not see this property because the ergodic components are given by ergodic affine transformations of finite dimensional terms. Right, so somehow
procyclic should be with rho affine.
Yeah, well, maybe at the end.
That's C prime.
Okay, so I have
conjecture C prime.
well, I have 10 minutes, right? Yeah. So I would like to show now, sketch how this is obtained, right? And just to see was it obvious from the very beginning, or was it not obvious? I mean, what we can just notice that we obtain countably many Furstenberg systems, right? We computed, but we know that we have uncountably many of them, right? So not all of them are described. But anyway, okay, and this 2 years ago, the paper was ready, so we sent to some colleagues, and from two of them we obtained in response the same question. So that's why you find it here. So can we find, a situation that what you obtain is just really a problem? And till today, nothing. Right? It's just a question of what kind of. I mean, it's not necessarily you in this class. Probably this is impossible in this class, I believe. But anyway, can we obtain something like that? Non-trivial nilpotent system product, Bernoulli and nilpotent non-trivial product.
So is this for logarithmic as well?
Yeah, well, both, right? Okay, so now what about?
But it's open already for subclass of Newton.
Yeah, well, yes. If you take Heisenberg, right? This we don't know, right? Okay, so what about how to prove this main result? So the proof consists of, well, let's say 3 parts. So one is probabilistico-ergodic, then there is, well, some kind of combinatorics, and finally analytic number theoretic part. So personally, what I like most is this first part, but that's better off. So if you have an independent, so all processes are stationary. Okay, so if you have an independent process, so then if you want to describe the whole process, you just should know what is the distribution of one variable. Right, that's everybody knows. But what happens if I have a process which is only pairwise independent? So that triples are independent, something like that. So this is what? How can I say what is this process? I would like to say, okay, this is a very precise process. Okay, so here is a proposition of that kind. So suppose, of course, process is the same as having shift invariant measures on this infinite dimensional torus. Okay, so this is the Zn. So we should think that, well, this is just Zn these are just projections on Zn is just projection on the nth coordinate. Okay, so what we do is just, so it's S1 valued process. Okay, so we start with, we consider the following sequence of random variables. We just take Z0, then Z1 divided by Z0, and then this is my new variable, and then again I take composed with Z divided, so just multiplicative compounders. And suppose now that after a certain time this process just finishes, right? So we obtain 1. So at the previous step, the function was just invariant. Okay, so that's the first assumption. The second assumption is that, okay, but on this step here, let's just assume that the distribution is uniform. So just Lebesgue measure on the circle. So you see, well, it's hard to, you have to jump between processes and the dynamical systems which you obtain from the processes. So in fact, so this second one should be thought of that, okay, my process will be very, very non-ergodic, right? Because you see that we assume that the distribution of this variable is just Lebesgue, so it's a very non-trivial function, but it's invariant. So the dynamical system is not ergodic. So just think that this is the distribution of this variable. It will be described as the measure living on the space of ergodic components. And this is, well, there will be something corresponding for the measure on the fibers, well, if you like. Okay, so then, so we assume that this is then for, of course, each variable is uniformly distributed on S1, and we see that this Z0, Zd are independent. And in fact, the measure which we obtain is just the measure nu d, which we described before, which was just the process obtained in the unipotent system. So that's the statement. Okay, so this is something you have to prove, right? So that there is to me, it was a little bit surprising that somehow you describe. So this means that you have a process at, I think the Zd plus 1 is a deterministic function of the previous coordinate, but it's given by a polynomial, right? And somehow we have to determine what these polynomials are, and this is the combinatorial part of the reason. So you can see, I mean, what's that we have a sequence of polynomials, which will somehow describe to us, you know, this more and more, this variables y, yd. And then you have to consider, so these are, so here the z0, these are just numbers of modulus 1, but you have also the associated polynomials, which you can see here. And the point is, what is it for? Right? So remember that the only thing which we are given is just our function, u. Right? That's the only thing which is available for us, a sequence. Okay, so we need a device, and this device is going to compute something. Right? We want to talk about the process Furstenberg systems, but we don't have them, right? We can manipulate on them, and but how to compute them? There is only sequence. So now, so the proposition tells us that if you want to obtain a property of your Furstenberg systems, you have to consider this kind of limits. So these functions, these are these polynomials divided by polynomials, these rational functions, and you have to consider this. And if you like to see the relationship, so for example, I want to show that this function is a constant function, right? I want to show that this function is equal to 1. But because this function is of modulus at most 1, so I can do it through computing its mean. But the mean, I know how to compute, right? I just writing the mean. Then I know that this is just this deterministic function of these variables. Now everything becomes continuous. I know how to compute it because, right, the point is generic for that measure. So I'm just writing this, and you see where does it come from? This kind of expression. So now the point is, okay, so that's a theory, okay, but now I have to compute this and show that this is really the case. And how to show that this is really the case? Well, so now it's just a little bit of number theory. You remember, let's go back to the definition of our functions. So our functions were defined by, you remember on the primes, it was something like p to the is n plus 1. But now we have to deal with all n's. But the idea is that this argument, of course, was used several times in their paper, is that in fact you can approximate these values for each n, like n to this power, and this will be true for most of the n, most in the sense of density. But because we are going to compute Cesaro averages, so then it's going to work. Right. So finally, what you obtain is that this complicated expression up to a certain error you can replace by trigonometric sums. And then you have okay, so you have to compute what is the asymptotic of that. And well, so here it's a classical Kuzmin-Landau theorem on estimation of exponential sums. And indeed, we just show that for certain sequences we can compute. Thank you very much. Questions?
Can I ask a small question? Can you go back to page 3?
3.
I wanted to ask it then, didn't want to interrupt. So
okay.
But it doesn't go modulo 31.
I don't know. You know, if you want to make it longer. So.
So, wait, 3, then show 4.
Okay.
Yes. These 3 proofs, the Chowla implies Cernak, are they similar?
I think the proof, okay, maybe Peter can add something, but if I remember the proof which is on the blog of Terry is just the proof
it's the same
of Peter, right? But there was no, I mean, in the article, right? It's 2000.
I have a handwritten note which I then sent. which is the same proof, but the dynamical proof I like very much because it is a tricky issue about generic points.
So you still can say that the dynamical proof is somewhat different.
As far as to be honest, I was asking Alon Lindenstrauss, why is this not standard in the dynamical world? And it's not. There is a paper of Furstenberg and somebody about generic points and disjointness and joining some like this. But you always have to make generic, and there's no assumption that the zero entropy sequence is generic. So it takes an argument. I think it does take some argument. And by the way, for a good number of years, Lindenstrauss kept on telling me this conjecture can't be true. And it was only after I saw that Chowla implied it that I said, I don't care what you say anymore, because I believe Chowla. And in fact, I have a question about that. In fact, Alon was telling me about all these constructions from the 70s by somebody from Stanford, maybe a student of Ornstein, of zero entropy systems, which look like positive entropy over long periods. I wonder if that construction of, you know what I'm talking about? You know, these zero entropy systems which sort of mimic positive entropy of
Student of
Ornstein. Yeah, I'll send, he sent it to me. I can find it. But I wonder if that construction has any similarity to this counterexample which Terry and Co came up with.
Yeah,
I'll find that paper. It might be, maybe there's some relation in that kind of argument. But anyway, when I was trying to formulate this after Green and Tau made the orthogonality to null systems, I was showing it to Alon, and he kept on saying, I've never seen what a bad zero entropy system is, and they can be very bad. And he gave me these examples that somebody had constructed of systems which mimic positive entropy, but eventually die at different scales. They mimic for a long time something, anything. They can mimic something at positive entropy, but eventually it has to die because they disjoint from positive entropy. So there's some interesting constructions there which might be related to this construction that you were explaining. It's possible.
So in 1 month, we have a conference. There will be a talk on Möbius disjointness conjecture. And this is a condition if and only if on the combinatorial level.
Very.
Who's talking?
Thierry.
Yeah. Thierry.
Thierry.
Are there other questions? Yes.
This question makes sense. So you have these different behaviors depending on whether you take logarithmic averaging or Cesaro averaging. I mean, there's a lot in between. Do your results say the thing if you average slightly more smoothly than Cesaro, but a bit less than logarithmically? Do your results belong to one or the other, or is the middle unknown? Or?
So it's a nice question, of course. And in fact, you know, if I remember correctly the result, so this is by a colleague by Michał Rams, and so they started averaging properties. So I think that if you pass from Cesaro to logarithmic, right? So let's say you would be divided by something like square root of n, you know, so then in fact these then you obtain completely equivalent.
Well, but
yeah, the first.
If there was Hardy scales, but maybe your question is about more general than Hardy.
No, this was your question, right? That I changed the way of averaging, right? But for some averaging, it's just the sequence.
Let me just add. So of course I care about such things a lot. The square root of n is just equivalent to Cesaro by general.
Yeah.
But I suspect that if you, instead of log-logish or whatever scales, go to slightly oscillate.
Then
I see.
Yeah, but I think this is not Möbius, right? It's just you have to decide first what can you say in general, right? About averaging with different ways.
But if I can modify your question, so suppose you ask a question in the realm of so-called Hardy fields, then I wouldn't be surprised that there is nothing in between.
Yeah, one over it. It gives you equivalent.
Either it will be equivalent or drop to low.
Can I make a number theoretic question about, comment about this logarithmic averaging? One of the difficulties in doing twin prime, say, is the parity principle, which intervenes parity problem. And by doing the average with log, you completely, the more you average, the more you weight the earlier pieces, the further you're going away from primes. So the whole point about this disjointness is that it doesn't require beating parity. If you want to do twin primes, you need to get some log gains, and then I think you'd face a very serious obstruction. So that's why this problem is approachable precisely, even maybe in Cesaro sum. But the minute you put log, it becomes much easier. So it's like Mertens, the sum of the asymptotics of sum of 1 over p up to x was known long before the prime number. So it's sort of moving away from the question about primes, but it is answering questions about configurations. If you want to get full entropy, which is a lot of progress, then you'd be welcome to do logarithmic averaging. So, it's a moving away from the parity problem. I just want to emphasize that.
Any other questions? Okay, so maybe let's end the talk here. Thank you again.